Let's get started then. Let me welcome you all. My name is Sandy Faber, and I'm one of the people involved in organizing faculty around climate issues at UCSC. And it's a great pleasure to introduce our speaker in Climate Salon number 2 today, who is Patrick Chuang from the Earth and Planetary Sciences Department. Patrick earned an undergraduate degree at the University of Alberta in chemical engineering. And he then went on to earn a PhD from Caltech in environmental engineering. He did a short postdoc at NCAR, the National Centers for Atmospheric Research, and then joined our faculty as an assistant professor, I assume, back in 2001. So I really come to admire very deeply the kind of research that Patrick is doing. In my trying to become familiar with climate models, I have learned that one of the major uncertainties of climate models is how aerosols interact with global warming, and specifically, how do they trigger or not trigger the formation of clouds. Aerosols are produced by human civilization, and some people have argued that aerosol production has delayed global warming up to now. That's a big TBD, and Patrick's research on the detailed dynamics of aerosol droplet formation in clouds, how this affects the structure of clouds, their convective structure and so on, is really at the cutting edge of this. So I was pleased to know that you are working to clarify what some would say is arguably the most uncertain aspect of climate models today. Given that, that focus of yours, it's not surprising to me then that you're also thinking on larger timescales and larger landscapes. And that's really what you're going to tell us about today. A future that's far different from what we see today in terms of energy availability and longer timescales perhaps too, okay? So again, learning about this topic, listening to many podcasters talk about global warming, energy availability, I really haven't seen another talk that's as ambitious as this title, in which the speaker actually tries to decide what the difference in lack of fossil fuels would make to human society. So this is a very ambitious topic, and I'm very honored to introduce you.
Well, that was far too kind. Ambitious might be another word for stupid. Yeah, okay. So anyone wants to chime in? Hopefully everyone online, you guys can hear me okay?
All good.
All good. All right. Thank you, Drew. So I think this journey started a long time ago. There's lots of people in the world to thank. Some of them are here, are listed here, and many of them are not. Okay, so I've given this talk once before, and I think I was maybe a little too alienating, so I'm trying to get into it a little bit in a slightly less alienating way. So the way we have structured current society, it's got an expiration date, right? One way to think of this is that our current society has a form of planned obsolescence built into it. That planned obsolescence is fossil fuels. So if you look over, so this is the x-axis is time from 6,000 years BCE to 10,000 years CE. And the point of this is that when viewed at this sort of like 10,000 year timescale, the fossil fuel era will be a very small blip, right? Hundreds of years is pretty much the likely story. It's very unlikely that we can get to 1,000 years, right? Even 1,000 years would be a blip on the scale of 16,000 years. Okay. And so the question is, what do we do after, right? After the fossil fuel blip, how do we plan the next version of society, preferably so it doesn't have its own version of planned obsolescence, so we don't have to do it yet again at some later date. Right? So that's in some sense, the main question of that we're trying to answer. So just to set the stage, kind of where we are now, just some basic ideas. I'm on the left. I'm the person consuming wonton noodles. I consume about 2,000 food calories a day, which turns out to be about 100 watts. So 100 joules every second of food powers my body, right? And then backing me as a member of the as a citizen, or not a citizen, as a resident of the United States of America, there are 100 energy equivalents of me out there working for me on my behalf. And this is true for every one of us in the United States of America, right? So there's about 10,000 watts up here per person, all the time working on my behalf. And if you look at it, the EU, the number is more like 43 human equivalents working on your behalf, and the global mean is about 24 humans working on your behalf. Energy equivalents. This energy comes mainly from fossil fuels, about 80%, that's on the left-hand side, and it goes into all the things we like: transportation, industry, heating my home this morning, the heat went on this morning, electricity to power the Zoom, among other things, right? So all the things that we like to do. Energy is also critical. This is an awesome figure showing that about half the world's food supply is done by synthetic fertilizer. So that's the red curve down here. And it meets almost exactly this green curve now, which is the world supported without synthetic fertilizer. In other words, half of us couldn't eat if we didn't have synthetic fertilizer, which comes from this high temperature, high pressure Haber-Bosch reaction to generate nitrate from atmospheric nitrogen. So energy is in our food supply, right? Half of us wouldn't be here otherwise. Besides energy, this, when I first saw this, was a shocking slide to see that each of us over our lifetimes consumes some crazy amounts of stuff, right? So fossil fuels are kind of new, right? 7 tons of phosphate rock, that's for fertilizer, phosphate fertilizer. 400 some kilograms of copper, right? 400 kilograms of lead. I still don't know where all that lead goes. Honestly, no clue. Bauxite is for aluminum. There's zinc, right? Like these are sort of crazy amounts. And the point is that our society isn't just energy, it's energy plus materials. So one way to think about society is that modern society is that we have inputs of energy, right? Doesn't really matter how, lots of different flavors of energy, plus raw materials, and that generates modern society. I want to modify this equation a little bit. We have to subtract off, to get modern society, you have to subtract this part in the bottom left. So I keep using this. I need to use this. No, okay. The bottom left, we got to subtract the energy and the raw materials that you need to obtain the energy and the raw materials. Right? So the energy it takes to run a power plant, or the energy.
Santa Cruz lecture on how to live without fossil fuels.
Okay.
Huh? I know that.
Fine. All right. So there's an overhead, all right, of energy and materials to get energy and materials. And then the other thing to remember is that modern society isn't just the stuff we make and use, but it's also about this other accumulating waste. CO2 is accumulating, microplastics, species are going extinct, etc. Right? So this is kind of the more full equation of modern society. And then the big picture is that we define the economy as healthy if and only if it is growing. All right, economic growth 2.3% per year is sort of the long-term average. This is a doubling time of 30 years. That's a really useful number if you want to put it in your head. But economic growth requires the growth of energy consumption and materials. So these two things, on the left is global GDP, its relationship to energy consumption. It's basically 1-to-1. And then material consumption and energy consumption also go basically hand in hand. Right. Okay, if we keep going the way we're going, one thing to think about is, okay, well, let's just keep burning fossil fuels. That's one option. I added up all the reserves, and they're on the top left. And the total proven reserves, it's a little bit fuzzy, but the proven reserves that are estimated is about 780 gigatons of carbon. All right, so we're at about here right now, right? So 2025 or 2024, right? So we've released about a little bit more than 500 gigatons of carbon so far. And the point is, there is 780 gigatons of carbon on the books of energy companies valued at north of $40 trillion. It is on their books. They have promised their shareholders, if they have shareholders, that they will dig it up and burn it, well, sell it for money, and then it will be burnt. So that's a big number. Yeah.
Those 40 trillion, do they like the costs to get the materials because they get?
That's the value. So the question, yeah, the question is what the $40 trillion really means. I think it's the value of this on the market. Yeah. Yeah. And then if we do that, if we were to take the 780 gigatons proven reserves promised to be sold and burned, and we did burn it, roughly speaking, we're talking about a mean global temperature increase of 3 degrees Celsius relative to pre-industrial. Most of the world is ocean and doesn't see nearly the same increase. On land, that's about double on average, so 6 degrees Celsius warming on land. That is 10 degrees Fahrenheit for those who don't think about Celsius. All right, that's the land warming, 10 Fahrenheit. Okay, this is not the same world. Probably not a place we want to go to. This 30-year doubling time makes math really easy. So about half the greenhouse gases we've emitted in total have been emitted since about 1990. Each year the math changes a little bit, but basically, so if we think about the emission of greenhouse gases between 1990 and 2020, just to make life easy, if we think of that as 1 unit, right, that is, then before that time, pre-1990 was another unit, right? And then the point is to maintain economic growth at 2.3% per year, roughly speaking, we're going to have to consume 2 units, energy, copper, steel, nitrogen, phosphate, water, etc., right, in the next 30 years. So whatever we did in the last 30 years, roughly, we have to do double in the next 30 years. And so think about that in terms of the resources we need, right? Every joule of energy, every kilogram of copper that we have been able to consume in the last 30 years, we need to match it with double that amount in the next 30 years. Exponential growth is voracious. All right, so how about we choose something different? This is probably not leading to a good place. So the conceit here is like, let's redesign the world so it can be sustained for the long term without planned obsolescence. I'll define the long term as something like 10,000 years or more, right, just for convenience. And then in my conceit, the idea is like, let's figure out where we can go. Let's determine what our destination is going to be. And then let's find a road to get us there. If we just start building a road willy-nilly, then who knows where it's going to lead us, and it might not lead us to a destination that makes any sense. All right, so first thing is let's identify this new sort of magic society, and then see if we can get there. And so the questions really that I want to ask are sort of, what are the physical constraints on this destination? what do we know and not know about this destination, and what sort of designs can fit? And I'm not going to really answer all of these questions, but I'll talk somewhat about some constraints. All right, so the constraint number one, I think, is pretty simple. And I had many more slides and I just cut them out. And it's like any person with common sense understands that economic growth requires the growth of energy and materials. Energy and materials are finite because our Earth is finite. And therefore, it must be true that economic growth is going to cease at some point. All right, so constraint number one is that we're going to have to replace a growth economy with a steady state economy, one in which we're not consuming ever increasing amounts every year. Right? Not 2.3% per year, 0% per year. That's the long-term goal. Now, how that works is a big question. If you don't agree with some of this, or you want to ask me about some of this, we can dive into some of the reasons this is absolutely has to be true. But if you don't believe me, you'll just have to sort of take it on faith for now.
Back up one.
Yeah.
I would accept energy from fossil fuels 0%.
Okay.
Does energy growth have to be 0%?
So energy growth, let's talk about it later.
Okay.
But yes, we're on a finite planet. Sandy.
I would accept that the consumption of resources is restricted, but we get into trouble with some people by equating that to the economy. So if we simply said, regardless of what you call the economy, money, finances, regardless of all of that, let's just focus on energy and material resources.
Okay, fair enough. All right, so Sandy's point is let's not worry about the economy and let's just talk about energy and materials, because some people don't like sort of this, what I'm sort of implicitly doing, which is drawing an equivalence between the two. I think they are exactly equivalent, but one might differ.
We'll take liking it needs to break, right?
The long-term goal is steady state, and then the road will be something else. Does that make sense? Yeah. All right, so I'm going to replace this picture with a slightly different picture. So let's just think about it as an accountant. All right, there are gross incomes of energy and raw materials in the top left. There's operating costs in the bottom left. And then the net is society. And at steady state, now that we've determined it's steady state, the nice thing is that this is zero. It costs us, but at least the nice thing is we don't have to worry about these things accumulating. All right, so we're going to start by talking about how much energy we can make, gross income, and then we're going to go from there. So constraint number two on this future world, that most of our energy will be solar and wind, which I hope to convince you of. And the question is, how much gross energy income can we produce from that? In these red boxes are the amounts of solar and wind and other things that are available at the Earth's surface. You can see that obviously solar is by far the biggest number. It's 83,000 terawatts. Wind is the next biggest, about 1,000 terawatts. All right, current human society, I listed on the bottom, is 20 terawatts. So the amount of sunlight or even wind is not really the limiting factor, right? It's not this fuel that is limiting us, at least over the time scale of a few centuries. The issue is that capturing the solar and capturing the wind requires materials. And it turns out that capturing solar plus wind requires sort of a lot more materials than we presently need or use for the fossil fuel industry. So the fossil fuel is on the bottom left, or the leftmost bars, all right? The point is they're small, and then when you get to solar and wind, all right, sort of on the right-hand side, those bars are big. So the material requirements for solar and wind are high, and the reason is very obvious to all of us, which is solar and wind are very diffuse. So you got to be everywhere, and that takes stuff. The other part of the stuff is that the amount of stuff, or our ability to get stuff, is harder and harder. This is copper ore over time. All right. And on the y-axis is the richness of copper in the deposits that we're mining. Right. So if you can't really read it, sort of near the beginning, so about 100 years ago, if you were a mining company mining copper, you would get about 2% copper, right, by mass, I think. Right. And now on the very far right, we're down to about 0.4% on average, all right, copper. And now I believe that mining companies are looking for deposits that are at least 0.1% copper by mass. So in other words, the quality of the ore that we're mining is decreasing over time for the obvious reason that we mined all the good stuff a long time ago, and we're going to the more expensive stuff now. Right. The issue is, of course, that this costs energy. Most of the energy in mining is in crushing rocks from big rocks to smaller rocks to smaller rocks. Smaller rocks to eventually expose the nodules of copper or whatever, so then you can get at it with leaching and things like that. So basically crushing the rocks down to small bits. And the fewer good bits there are, the more rock you have to crush, so the energy scales accordingly, quite obviously. The other problem is that as the copper ore degrades in quality, the nodules actually get smaller. And so you actually have to crush the rock to a finer and finer scale in order to expose it. So it's kind of a double whammy. And so this is the top right curve is the energy requirement of copper as a function of the ore grade. And so as the ore grade decreases, the amount of energy goes up rapidly. And on the bottom right is the amount of waste. Of course, mines produce lots of waste, right? The amount of waste, which is all this waste rock that you've crushed and now discarded, 99 point whatever, 6% of it, right? Increases very rapidly, right? So this is what we're fighting. And so I think there's a really great quote here from Barty. It says, the limits to mineral extraction are not limits of quantity, they are limits of energy. Extracting minerals takes energy, and the more dispersed the minerals are, the more energy is needed. So basically, it's going to get harder and harder, more energetically costly to mine copper and other things. And all right, we'll just skip that. Okay, so let's just ignore all these facts. Say, okay, we just magically managed to construct a solar plus wind energy infrastructure to replace the fossil fuel infrastructure, right? Let's just say we managed it. It looks like solar panels and wind turbines and say batteries for storage. So we say, congratulations, well done, team. Unfortunately, we're not done. Now do it again over the next 20 years. And that's because that's the estimated lifetime of solar panels and wind turbines and batteries, roughly speaking. So Alice Friedman, who we think was supposed to come earlier, we think is going to come in the winter, right, Sandy? She wrote in her great book, Life After Fossil Fuels, that wind turbines and solar panels are rebuildable, not renewable. So the fuel is free, the photons are coming all the time, but the energy infrastructure is rebuildable, right? Every 20 years. This is a big feat. So this constraint then on energy, how much energy can we make? It really comes down to how much can we rebuild every 20 years for 10,000, 20,000, however many thousands of years you want to think about. It's a big deal. I don't have an answer, but I think this is one of the constraints. It's like we need to think about having this energy infrastructure that's not permanent, but has to be refreshed every 20 years. All right, so we talked about energy now, right? The gross income of energy really comes down to raw materials. So we're going to talk a little bit more about raw materials, both the gross income and then the operating costs, and then we'll talk about energy to sort of finish.
Wait, to it, but do you have a sense of in that 20 years, rebuilding that infrastructure?
Yep.
How much of that infrastructure was expended, as in fully lost from the system?
Yeah, I mean, it's got to be a relatively small fraction. So the question Jason asked is how much of the materials of, say, a solar panel is lost during the 20 years, and how much is just there, but just sort of degraded in its sort of physical chemical properties that could be recovered or recycled, right? Yeah. I mean, my assumption is, relatively little is totally lost, right? There's going to be some corrosion and other things. It can't be zero, but it's probably a pretty small number. Yeah. All right. So another constraint is that there's only a finite amount of raw materials. The big graph, the one with the colors, that is sort of the projected production of copper, and it runs out to 2100. So that looks suspiciously like the curve on the top right, which is the fossil fuel pulse. This is now the copper pulse, right?
How did you get those?
Oh, stole it from the internet. I can find the source if you want. It's a model of production.
It's a guess at future.
It's a guess at future production.
Based on current.
Yes. Yeah. So not good, right? Because if we just rebuild this and then we have no copper, then life is in trouble. So I think what's obvious to me is that recycling is going to be absolutely critical to our new society. We have to recycle very, very, very carefully. This is a sort of periodic table. The pink colors are the elements that we recycle at less than 1%. The sort of the darkest colors are the ones that we recycle at greater than 50%. For the most part, we do a good job with aluminum and iron and copper. Those are the three that we actually do the best jobs with. And then the others kind of so-so. One of the constraints on recycling itself is that when you think about recycling, you actually have to unmix the materials to get sort of a raw material that you can reuse again, right? And so unmixing costs energy. And so complexity or mixing is the enemy of recycling. So one interesting idea is like, well, you might not be able to have a cell phone out here or a laptop because these are extremely hard to unmix. Maybe we have to just build things that are easily recycled, right? Not highly mixed, to make it so that we can recycle. And then who regulates this? Who decides that we can and can't mix something because it's too mixed up or too hard to recycle? So optimistic projections of recycling. So here's just a graph of where if you just collect some, say, nickel. So sorry, I keep using this mouse, but it's not on here. Oh, it is on here. Okay. So if you just choose a sort of brownish color, that's just some random nickel source you collect at 80%, which is typical. Then you pre-process and then you end process. And then in the end, you get about 60% back. So you had 100% to start with. After all the recycling, it was 60%. So it's not possible, of course, to recycle 100% efficiently. Optimistically, maybe 80% is probably the best we could do. But even at 90%, all right, you take 1 kilogram of, say, copper, and you'll end up with 0.1 kilograms of copper after 22 cycles. Take your solar panels, you recycle it 22 times, you've got 1/10 the number of solar panels you started with, which is about 400 to 500 years at 20 years per solar panel lifetime. This is not meeting the sort of 10,000 plus year goal, right? That's another form of planned obsolescence. So we still need new inputs somehow. We need to find new ways to find materials. I don't know what the answer is. There is, of course, asteroid mining. There's a great study where they've estimated how many trillions of dollars it takes to actually grab an asteroid and bring it to near Earth orbit and turn it into materials. Well, maybe that's where we have to go. The moon is much closer, is much easier to deal with. So the moon is, of course, not everything that we need, but the things that we can find on the moon might be useful. But of course, the overhead, right? There's an energy cost and a materials cost of building an infrastructure to harvest asteroids or whatever. There's other things that would probably be ecologically just devastating, like seabed mining, but also things that are beyond conventional mining. Okay, so I would say that raw materials are finite, so our gross material income depends greatly on recycling. Just for sure, 100% recycling is critical, and then we will need new inputs to maintain steady state. And then our net material income. So how much materials like copper we have left over to build cell phones or lights or whatever depends on how much copper we used to make solar panels and wind turbines and the new power grid. That's the overhead. Okay. So we've talked about gross income of energy and raw materials. So let's just talk about the last bit here, which is the operating energy cost. So how much energy is being siphoned off to make energy and raw materials. So what are our expenses before we can give the extra energy to the rest of society? This is often quantified using this very useful concept called energy return on energy invested. And it's basically just how much energy you produce divided by how much energy you spent to get that energy. And way back in like 100 years ago in Texas, all you had to do was stick a pipe in the ground and oil comes gushing out and the energy return was like 1,000 or more, all right? So for every joule that you spent building a pipe and hammering into the ground, you got like 1,000 joules of oil out of some deposit. Nowadays, it's not quite so simple, right? Nowadays, the energy return on energy invested is probably somewhere between 10 and 20. So here's 10, here's 20. Solar itself, solar panels are estimated to be about 12 to 14. All right, and you can see why this is important, right? That obviously if you hit one, your society is over because all you're doing is spending energy to make energy. Sandy.
Just the point that we do have to take into account the cost of distributing the energy.
Oh, yes, coming, yes. So Sandy's point is that there's other energy costs that are not on here. And that is completely true. But just to talk about energy return on energy invested, there's this idea that, it's actually on here, there's this idea that to support sort of modern society, we need a return something like 10 to 1, give or take, right? That's what we need to maintain society, right? So the net energy has to be something like 10 to 1. I'm going to skip that. And then this is the caveat that Sandy just mentioned. This figure only describes energy production. Right. So what are some of the other energy operating costs that we'll experience? Well, one of them is energy storage. As we well know, the sun doesn't shine all the time. The wind doesn't blow all the time. To store 1 barrel of oil energy equivalent, if you want to do it as oil in a tank, it costs about $1 US to store 1 barrel of oil of energy. Right? It's pretty simple. If you want to store that much in electricity, it costs about $200 US for this battery bank. 1 barrel of oil costs about $70 US right now. That's why we don't worry about storage. It's in the noise. This means that the price of electricity goes up by a factor of 4. Right? So that's a big deal. But it's not about money, right? It's about what this money tells us. That's what the cost is of producing the materials in the battery. The overhead is tremendous. Another example of an overhead is that liquid fuels are indispensable. And if you listen to Sandy's last climate salon talk, it was very clearly covered this. The point is, we're going to need a certain amount of liquid fuel if we want to do certain things, like mining. You need a heavy-duty vehicle to mine. To run that vehicle, can't do it off of batteries. You need liquid fuel. So we're going to have to make liquid fuels. Unfortunately, making liquid fuels from sunlight is a very low conversion efficiency. So you take, say, 100 joules of sunlight, and you might get like 10 joules of liquid fuel out of it. So, but there's no choice, right? At the moment, at least, we don't know of any other way to do this. So here are some of our main energy expenses. We're going to have a lot of expenses. We're going to be mining lower concentration ores, which means our energy costs go up. We're going to have to unmix for recycling. We're going to have to build and maintain energy storage. We're going to have to convert solar into liquid fuel conversion. And then we're going to have to clean up after ourselves, by the way, which also costs energy. So all this and way more, this list could be 200 things long, I'm sure. All right, the point is our energy expenditures are going to be a lot bigger than we sort of currently totally appreciate. Okay, so if I were to sort of sum up the constraints, I guess, I would say that a society without planned obsolescence is one that has sort of a set amount of net energy and a certain amount of net raw materials, both of which are constant over time. And you determine those numbers by figuring out, okay, well, how much gross energy can we build? Gross energy depends on the rebuildability of solar plus wind. The rebuildability depends on raw materials. The raw materials depends on recycling and new sources. And then to calculate net energy, you have to account for our overhead expenditures like mining, energy storage, etc. And then the net raw materials, in many cases, depends on what our overhead expenditures are. In other words, how much we choose to rebuild. Because every time you rebuild a solar panel, that's copper that isn't being used for something else. So those are the constraints, the one constraint to rule them all. All right, so let's go here. So the one constraint to rule them all is none of this matters. If we just continue to grow, nothing we do matters. We'll just run out eventually and the whole thing just collapses. That is where we're headed if we don't do anything else. So the question that sort of sits topmost in my mind and for which I have literally no answer is how do we change the steady state economy? No idea. No clue. But within the constraints of net energy and net raw materials, which of these destinations is possible for a future society? I'm pretty sure the Jetsons-like thing down the bottom right is not possible. If you ask me to guess, it's probably closer to the Wild West than it is to sort of modern day Budapest, which is here. Maybe if we're lucky, somewhere in between. I don't know. Maybe it's modern day Wild West with good telecommunications and good hospitals. Maybe that's the best we can hope for. I don't know. All right. And then I would end it there, but then I do have a little bit of extra time. So here are my best guesses of our destination. All right. These are just purely from feel. There's literally there's nothing rigorous about any of this. It's just me sort of like sticking my finger up in the air and taking a guess. So global energy production, my guess is we're running currently 20 terawatt society. Maybe we can generate 2 terawatts. Rebuildable all the time, maybe. However, it sounds okay until you accept that our energy return on investment might have to be much lower. Right now we're at something like 15 to 1, somewhere between 10 and 20 to 1. I think down the line, our overhead is so high. I think this has to go down a lot. So maybe it's 2 to 1. So our net energy production is 1 terawatt. I think our per capita energy will probably be at least 10 times a present day member of present day American or resident in the United States. That seems pretty reasonable to me, actually. And if you take this number, 1 terawatt, and you divide it by 100 kilowatts per person, you end up with 10 million people, which is a pretty small number. But anyways, these are my guesses. If you ask, if one was interested in my guesses, these are my guesses. And then I think about like half the people work in mining and recycling. I think that's what our jobs are. All right, I will stop there. Thank you.
explain the WAG about energy costs per person, that for endless.
Yeah, that was interesting.
Oh, so we are at 10 kilowatt.
And a factor of 10, I would have thought we'd become more efficient, not less efficient.
Oh, but so right now, so in a simple example is if we had to clean up all the CO2 after ourselves, right? Well, actually, we would be in energy debt. We would actually not net any energy right now. But the point is, we're not even cleaning up after ourselves. So waste is accumulating. So just by like saying you have to clean up after yourself, get rid of all the waste
The extra cost.
is a huge cost. And if it's 90% of the energy you're generating, then there's a factor of 10 right there. Right. But it's all of that. Like that's a simple example, but it's kind of all that stuff that we're not doing now. Yeah, but it's also things like going to hit an asteroid and pulling it in.
Yeah.
It's a lot of energy, I think. And if it's not energy, it's materials that embed energy in it. And so, yeah. Is someone handling online questions? Carola, can you handle?
Yeah.
Okay. Okay, cool. Yeah, Sandy.
So I think you've shown that wind and solar are not the wave of the future.
So Sandy says that wind and solar are not the way of the future. Okay.
And since energy is absolutely key, what of the sources do we currently know about that actually
I love this.
the prospect?
Thank you, Sandy. So this is the question known as, what about nuclear? Right? That's the question.
That is correct.
That's the, what about nuclear? All right, what about nuclear? Love this question. What about nuclear? Okay, two problems with nuclear. So we're talking about fusion because everyone wants to do fusion. You want to do fusion? Okay, well, we could do fission. This is the issues are the same. All right, but if we talk about fusion, which is always 30 years in the future, right? Fusion always sounds like hydrogen plus hydrogen equals helium plus a hell of a lot of energy and life is great. Fusion is not hydrogen plus hydrogen equals helium. Fusion is actually deuterium, isotope of hydrogen, plus tritium, isotope of hydrogen, equals energy. Right? Tritium in a fusion reactor comes from a very unplentiful isotope of lithium, lithium-6, which is about 5% of all lithium on Earth. This is a fuel. We burn it, it would be gone. Alternately, if you're talking about like the French ITER reactor, tokamak style, all that tritium comes from essentially, as far as I can tell, two nuclear facilities, fission nuclear facilities that run CANDU nuclear reactors, which are the Canadian nuclear power reactors, outfitted with a special tritium separation unit. Each reactor produces 130 grams of tritium each year. One fusion reactor is estimated to require 1 kilogram of tritium per week. That's a lot. Turns out we don't really have a lot of tritium around. In a fusion reactor, the idea is kind of insane. It requires an efficiency of, doesn't really matter what, but there's a process which requires an efficiency that's basically 99.999999999%. Otherwise, the whole thing shuts down. But ignoring that, it's just using this as fuel. So there's a fuel problem, but there's another problem, right? It's not just a fuel problem. Fusion and fission produces neutrons. Neutrons are captured by the containment, the container of the nuclear reactions. Fusion or fission doesn't matter. In fusion, the neutrons aren't subject to the magnetic confinement, so they go flying out. They hit the sides. They turn the housing radioactive and brittle and eventually has to be decommissioned. Otherwise, the whole thing breaks apart and nuclear stuff goes everywhere. And so you have to rebuild it. So fusion is potentially also only rebuildable, but it can't be recycled because the whole darn casing is radioactive. So you can't even recycle it. But now you might be in a worse place where you can't even recycle the stuff when you're trying to rebuild it. Right. So what about nuclear is, I don't think nuclear is going to work. That's my claim. Sandy.
For reactors.
Yeah, I mean, you can breed existing uranium. You can stretch the current uranium supply out by a factor of 100. You still have a containment problem. You still have the materials that you make the reactors out of problem. and that stuff does not become unradioactive. So you can't rebuild it as easily, right? It's a problem.
The calculation that you showed us, where you showed that, basically this measure is almost for 5 million people, is that assuming that you do nothing, basically?
But you clean up after yourself.
You're saying everything you admit, right? I mean, maybe that's too tight.
Sorry.
I
So the question was,
think that would trigger that. Still, I mean, but
yes, yeah, okay, so that's a great, so the point was, I think the greater point is about having no waste, right? And
I don't know if you need that.
you don't need it. So the natural biogeochemical cycles of the earth will sort of naturally recycle things on a long time scale. You know, hundreds of thousands of years, let's say. It depends on exactly what, but
I guess my point is that maybe this is like a pseudo steady state, right? Something.
yeah, that's fair. That's fair. Right. So the point is, it's not perfect steady state. It's maybe pseudo steady state where, you know, you're talking about, you know, 90 something %, and then the last few percent you try not to worry too much about. I think that's totally fair.
When we really talk about these 10,000 years timescales, I do want to be a bit more optimistic with nuclear fusion, because what you said, like about the material being necessary materials, that's just because that's the easiest type of material.
Correct.
It is in principle, I mean, the sun does it, it's possible to fuse 4 protons into a helium.
Right.
Then you also don't have neutrons as waste product. It's
Right. Yeah.
more pressure and more temperature needed.
Yes. So yeah.
We're not gonna get there in the next like 100 years, right?
Right. So the question was that basically the comment was that there are other fusion reactions that are aneutronic, and so you don't have this problem. The problem is that the activation energy for these aneutronic fusion reactions are much higher, so the temperatures are much higher, and we can't even do this easiest one yet. So what are the possibilities of doing those and net a decent amount of energy, right? So, but the point is, theoretically, it might be possible to achieve aneutronic fusion. Yes, I agree.
Well, I have to say, I had a number of very sad responses listening to this.
Okay.
First of all, to move from 8 billion to 10 million means a lot of people are gonna have to die.
Well, people die all the time. Sorry, the question was how we go from 8 billion to, or that going from 8 billion to 10 million is not a fun process. And my point is, well, people die all the time. It would be a very difficult transition, no doubt.
Second of all, seriously proposing a steady state economy.
Right. So the other comment is that there's no political entity would propose a steady state economy. Also true.
So I'm wondering about that. As a political sociologist, I'm wondering.
I mean, I'm a physical scientist. All I'm going to say is you can try to continue growing, but like you can't.
Collapse.
Yes. It's
If
gonna,
we're talking about collapse, I've looked at the literature. Tries to understand why societies collapse. A lot of different explanations, but a paper that I read recently kind of boiled it down to 2 things that all such collapses seem to have in common. One was a society that overuses its natural base
okay.
resources, and second of all, characterized by such inequalities
Right.
that the privileged elites hang on to their privilege as long as possible until resisting any change until it's too late.
So the comment is that past societies, right? Past societies have collapsed, and the 2 sort of unifying ideas seem to be one, that we overextend ourselves on resources, and then 2, that there's a sort of wealthy class that continues this until the whole thing just falls apart. So I believe you. It seems natural. Should we go to online questions?
One comment.
And Sandy wants to make a comment.
Andy, could you share that paper with us? That you sort of boiled it all down into simple arguments?
I think I have a copy of it.
Okay.
Thank you.
So Andy will share a paper that's about societies collapsing. it's nothing but fun news in this. Yeah, these are great. Yeah. Caroli, are there questions online or did people? Okay. Oh, David has his hand up.
Yes, my question is actually pretty simple. It's related to your conclusion that we can support maybe 10 million people. Has anybody estimated the number of people that's required to reach different levels of, call it, quality of life or civilization, et cetera? And I mean, we may be between a rock and a hard place where you need at least 100 million people in order to even have the diversity of skills and social needs, whatever it would be. Has anybody studied that part of the global picture?
That's definitely not my cup of tea. I don't know if anyone in this room or anyone online knows if we studied sort of what is a reasonable minimum number so that we have sort of a society that we're happy with.
Yeah.
I mean, we put up already have healthcare, things that extend your life, average should be 5, 7.
I'm sorry, I couldn't hear the answer. It was very
Yeah,
faint.
yeah, it's impossible.
I'm saying that, basically, the question is about the availability of resources you have.
No. I think it's about like the human experience of living in a population that is, 10 billion total versus 8 billion.
But how do you?
Well, I don't believe the 10 million,
No, and I don't necessarily believe it either, but I'm just saying that, this is one way to view it. But the point is, I think, how do we what does it mean to live as one of 10 million in the world total? And is that a qualitatively different experience?
Is there critical mass
Right.
for modern society and
Is there-
moderate level of technology as we currently know?
Right. Is there a critical mass in order to sort of maintain a diversity of knowledge and experiences that makes us sort of want to be a member of the society? And it's a good question. It's a good question, David. I don't know the answer.
Okay, well, I didn't necessarily expect a definite answer. I was just wondering whether anybody has studied this issue to balance out your rather I call pessimistic view of what the steady state would be.
Yeah, and am I being purposely pessimistic? Yeah, maybe I'm being
Sure,
maybe a
be
little bit.
that's good. You need to be.
But I would be shocked if the answer is more than an order of magnitude bigger than this. That's what I would say. I would be very surprised.
I mean, let's say 100 million, right? Would be
Yeah. Right.
That's about right.
That's what Sandy thinks as well.
Andy was mentioned there are no political actors that will entertain sort of a steady state economy. Are there any political bodies that are even listening to these predictions? Say, okay, there was something that we need to start at least thinking about.
So the question is, are there any political bodies even thinking about sort of the end of growth? And the answer has got to be no, right? Because growth is sort of like the universal band-aid on any problem. It's like we grow ourselves, there's poor people, we grow ourselves out of this problem. There's inequality, we grow ourselves out of this problem. So that's kind of always been the thing. And if you just take away the universal band-aid, then you actually got to do real change, and that's got to be a lot harder.
Yeah, well, you get now to the point where you have information and some data that shows it's not working anymore.
Right.
I think people think that's what happened. I think they don't care. That's the problem.
Right.
It's a very nihilistic way of, they don't care.
Okay, so where is
So-
the wall?
So I think the point is nobody really cares enough to listen to the very small minority of people who are sort of saying these things. But people have been saying these things for a long time. There's a whole field of economics called ecological economics, and people have been sort of thinking about this problem for many decades. This is not new to me by any stretch of the imagination. So, yeah, but
Predict that. What would you say? Where's the wall? 50 years, 100 years, 200 years?
you want to say it, Sandy?
I think the first symptom is going to be a reduction in economic growth because the cost of producing materials and energy is going to climb. And we've seen that with the current model, the amount of flow through of those materials is roughly proportional. So what happens to an economy in which the world is increasing its supply of cheap, that's key point, cheap energy and materials at 0.5% a year instead of 2 or 3% per year. So I'm wondering about a readjustment of the financial situation before we see a major readjustment of the materials situation. So to put it bluntly, isn't it true that to save for your retirement, we've all implicitly been assuming a growth in the economy at 2 or 3% per year? What happens to endowments? What happens to pension funds? What happens to bond markets if the economy doesn't grow? That's, I think, the first symptom that I'm worried about.
And I would say I'm no expert in the financial stuff at all, but Nate Higgins would tell you the first symptom is the growing debt of governments, because the growing debt, so a debt borrowing something is basically promising to spend future energy. And this only makes sense if the energy inventory is growing over time. And as the debt grows, it means we're sort of pushing this promise deeper and deeper into the future because we're not growing the inventory as fast. And so I think the first symptoms are already here. And Sandy.
There is another way of dealing with debt, and that's to inflate it away.
Okay.
And so I think, in my view, there are really two separate problems. One is kind of imaginary. It's the worth of the dollar versus raw commodities.
Mhm.
And if we just simply devalue the dollar, the debt becomes much smaller and we don't have to worry about it in real terms.
All right.
And that will produce another social crisis. I would argue that Biden-Harris lost this election because of inflation. I mean, the Democratic voters hate inflation. And any administration that wants to stay in power is strongly moved to avoid inflation, but at some point in a few years, I think we will have to inflate.
Right. So I can't repeat all that to all those online, but I'll answer the question in a different way. So the question is like, what's the time scale for things starting to unravel to the point where maybe there's enough motivation to change? And I'm not good at this, but I will say, what's his name? The guy who works at Apple, who lives in Santa Cruz. You know who I'm talking about. Anyways, there's an article. He says, the title of the article is 1 billion people will die by 2035. So there are people who have thought about this, and I'm not saying I endorse it or not, but the people who thought about this, that sort of the cascading failures of the system are sort of 10 years away, and it will be bad. If I were a guessing person, I would set the over under 2040 maybe, and I think we'll start to see really bad things happening before 2040. That would be my betting line. But again, I don't know squat. All right. Start here.
No, I don't think it needs to be that way. I understand what you're saying. But we know that, for example, education and etc. increase standards of living will lead to population growth, right?
Right. The comment is it doesn't have to be this way.
Thing is, at the same time, you have government incentives to slow down property because, well, it leads to also economic growth. When they're kind of correlated with the population rate.
Yeah, I mean, but I think the point is, right, like no politician worth his or her salt is going to tell us to start shrinking, right, without a reason.
I mean, I don't know if it's going to shake very quick, but
Fair enough.
see that probably we should be thinking about scenarios at this point. So one of the comments I have about it talk is like, this is nice, but this is kind of maybe on purpose, detached from scenarios. But I think when we think about alternatives or energy, we should be thinking about the conditions in which these alternatives will need to be developed, and those conditions are going to be collapsed in society. I mean, it's not. This is the thing, right? The thing is going to collapse one way or the other, either in a controlled manner or very not controlled.
Yeah.
And the economy is going to shatter.
Yes.
Way with the other.
So the point is modern society is going to change, whether it's in a glide down to the runway or a crash landing into the runway. Yes.
And you've got to get political actors not responding to the situation. I do think it's just that a lot of them are from here.
No, they don't, no.
I think they probably no, just that they think that this is maybe something for the future. They're going to be dead and they're
Well.
there.
More than they did not know, they don't work.
No, they-
Right.
Yes,
Good.
I mean, maybe you go ahead first, because,
well, on the don't know question,
Some people
is
know.
this not being worked on at the Department of Energy? It seems like this would be, you'd have a,
Right.
right, it may be a secret, but you would have a team.
So the debate is now devolved. I would call it devolved into governments today, which are, for the most part, bad actors in this. So again, yes, I purposely wrote this, made a talk that was completely divorced from reality on some level because we need to figure out what destinations are available to us before we just start doing stuff.
That's right.
If we start doing stuff randomly, who knows where we're going to end up, right? We could end up in just as bad a situation again. All right, he had his hand up first, and then David.
I'm gonna contribute to the devolution of the debate.
Oh, man.
I have this thing that makes me very, very depressed, which is, I think, right, this waiting for the ball to hit the wall is gonna lead to us necessarily crashing, because you see that already, right? When things get tough, people
Right.
resort to isolationist populist movements.
Yeah.
And the US is never gonna say, oh, we're gonna stop growing as long as China and Russia are growing. And the same happens with that, right? So we need an international community that is trust-based and that actually acknowledges these problems and is like willing to stop this international competition.
Right.
That's both
So
economic and military and everything, right? And I just don't see that happening.
Right. So to sum up the comment, to change the way society works requires everyone to trust each other and work together, and we're going in the opposite direction. That's I think a summation.
Basically, so I'm now hoping for maybe is that wrong?
There seems to be broad consensus in the room that is true. All right, David.
Yes, I want to say that one of the motivations for this whole program was the Earth Futures concept. And if you look at 10,000 years in the future, it's not clear that we even have a direction or vision for that. I mean, I'll just toss a few ideas. With artificial intelligence, clearly you can create, creatures that probably maybe as inventive and creative and fun to be with as we are as biological creatures. And maybe the end point after, say, 10,000 years, 20,000 would be that humans try to achieve preservation of its culture and its technology, etc., but doesn't require, even 8 million people to do that. Maybe 1,000 people with, I don't know, 1 million robots and etc. would keep our world in a good state where biodiversity and the things we think are precious of our Earth are preserved, and who cares about the people who go to other planets and blah, 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 blah. But the point is that if we have a different target, which doesn't require an anthropomorphic economic growth, i.e. more and more people, in some ways, we have a very different path towards what you may call a sustainable one, right? We have a target that we want to preserve our civilization, our culture on the time scale of 10,000 or longer years from now, which may or may not require, all kinds of new technologies, etc.
Yeah, well, we net energy, and we have a certain amount of net energy and a certain amount of net materials that we can use. And if you want to build robots and power them, then
I understand. I didn't say I want to build a lot.
And I'm not saying yes or no. I'm just saying it's a choice we make. But again, robots wear out, and you got to replace them.
Oh, yeah, sure, of course.
So,
that's why I said a few, right? I gave 1 million robots, right? I said a small number of people. So I wanted to keep it within.
But what is why cost? Does that mean? Right. Well, but does that mean there's fewer MRI machines or whatever there is? Fewer centrifuges to make vaccines and whatever else it takes, right? These are all trade-offs.
Right, agreed. Thank you.
No problem.
So, I really enjoyed this presentation, it was great.
Thank you. But
But it's like, okay, so you're thinking about this,
Mhm.
okay? Sandy's thinking about it. Who else in the world is thinking about this?
there's a bunch of people. Yeah.
Like, where
100 people.
how is this happening?
All right. Sandy's estimate is about like 100 people are thinking about this. That's probably about right.
But for the qualification, there may be thousands of people who are thinking about various aspects of things. But the number of people who just put all the pieces together the way we tried to do in this room today, thank you, Patrick, I would say, and see the implications of that integrated picture, it is about 100. And the reason I say that, there may be more, but they're not saying anything. And so if they're not saying anything, they don't do any good. I'm talking about the people who are expressing opinions, and from their opinions, it's clear that their minds have reached this level of insight, conclusions, etc. They're mostly people who are writing books and are on podcasts. And I would say there's no more than 100.
Yeah, that'd be true.
And how do you know then about expanding that?
I wish I knew. So maybe we can talk about that, because I've been stymied here as trying to, do something with the Earth Futures Institute. Exactly what is it that you can do that's helpful? So we should move the conversation.
So I'm going to repeat. I'm going to repeat the questions. I think it's important even for the people who are not here, which is, yeah. But the question is, how do we expand the number of people who are thinking about this problem in sort of a integrated way, right? And I'm not saying that my way is the only way, but I'm saying it's like viewing the whole of society, I think, is a useful way to look at things. And I think there's at least some consensus in this room that we should expand. And
Sitting next to someone who's been in the National Academy. Why is this not a report of the National Academy?
It's a very good question.
oh, that's a great question.
Yeah.
So
Figured that.
X proposed making this a report of the National Academy. That's a cool idea. That's a very cool idea. Have we checked who the next head of government is? I don't know. I don't know who's the boss of the National Academy, but Marcia Minette, all right, former UCSC Earth and Planetary Sciences Department faculty member. All right, let's just let everyone go, and then if there's more to discuss, you can email me or Sandy or volunteer to give a talk. And yeah, thank you guys. Thank you everyone who was online.